Hello everybody. So this video is going to be in English, so I'll say just a few words in Portuguese for my Brazilian audience before continuing with the review. So, pessoal, esse vídeo eu vou fazer em inglês porque não tem ainda review em inglês desse equipamento na internet. Então, como esse vai ser o primeiro review completo, assim, sem ser do fabricante, o fabricante fez um review em russo. Então, eu vou fazer em inglês para ver se a gente consegue atingir uma audiência maior. Alright? So, back to English. This video review is about this device, which is a 2-port VNA, one path, though. This case is all made of plastic. The company that manufactures this and sells this on Aliexpress is ARINST, right? ARINST. This is a VNA from 1 MHz to 8800MHz. It's quite a very large bandwidth. And I think for the price, I got one of these for $343 on the 11th of November promotion on AliExpress. And it's quite a device. It works up to 8800 megahertz, right? 8.8 gigahertz. Of course, when I got this device, I had to buy a calibration kit. I also bought the calibration kit from AliExpress. There was someone there selling this calibration kit that goes up to 9 gigahertz. So you can see that they actually have the device and an SMA adapter. Let me focus on here. So the adapter is on the edge right here. So it works, the calibration kit. Also, they come with the through, which is just an unknown through, right? Which is a double male and a double female. Just an SMA little adapter right here. I will use some SMA cables to demonstrate the use of this. It's very, very simple. It's the simplest VNA I've seen. It's got less features, softer features, as to say, than the Nano VNA, which is quite popular. The back of the device, you've got only a USB, right? USB connector and nothing on the sides. And in the back, just the screws to open it up. And here is the 2 ports. It's just an SMA adapter at the output right here. I think it came with the from the manufacturer like this. So it's a male SMA natively on the board. But I think the manufacturer just sent this very tightly screwed into here. I'm not going to take it out, but just to protect the original device, right? So I just let it like this. So let's do some experiment with it, right? Let's see how it works. But before doing some experiments, I will show you the block diagram that comes with the manual. So the box is a very simple box. As you can see, I've got this, $340 for an 8.8 gigahertz VNA, 2 ports, right? It's just, taxes, forms, and, it's a very simple manual. And I downloaded the PDF from the internet, from the official website. So I'm going to show you the block diagram, and I will show you on the Tektronix spectrum analyzer how this works and how the signal quality and how the tracking generator of this VNA is. We will analyze the signal, and you'll see that the first time I saw 8.8 gigahertz, I immediately thought about this little guy here. I'm going to show you in a second. So I immediately thought about this guy. So it's a PLL from analog devices that generates 4.4 gigahertz, right? And I had this for a long time. I've got some videos in Portuguese from my Brazilian audience in the channel talking about this 4.4 gigahertz generator. And when I saw 8.8, well, okay, you've got a high-pass filter, you got the second harmonic of this, and then used it to sweep in frequency to get the 8.8 gigahertz, right? And I believe this is actually it. That's how it's implemented. So I will show you on the block diagram that it's exactly something like this. It's not exactly this yet because I didn't open it up. And I don't plan to show it the inside very soon. Maybe when this video is recorded, I've already opened it up. And you might see some images of the internals of this device. But it's basically a very, very simple device. The manufacturer provides pictures of the inside on the actual original website, so you can get access to that. So there's no need to open it up. But it's quite simple. And it's very, very smart to do this type of device and sell it on the market right now. Really good. Let's go to the block diagram. So here we are with the manual downloaded from the official website. Crux, I believe, is the name of the company. I don't know if that's in Russian language. I don't know. But I always see in all their instruments this ARINST name here. So this must be some brand that it came up with. And here's the picture of the device I just showed you. 10 dBm on each port for maximum power allowed. Going directly to the block diagram of the device. This is pretty amazing, right? This block diagram is a very, very simple block diagram. And you can see it's a good time to be alive, right? You can build a device like this, 8.8 gigahertz VNA with very cheap components, very cheap parts. The generators for the local oscillators. But those generators, the good thing about them is that you don't need them to be very clean, right? Because they're tracking generators, okay? And you can, low pass filter everything in the end and do some programming and then, selecting the frequency, the resolution bandwidth that you want, and then stream that to a processor like this. So the STM32 here, let me zoom in right here. This could be something I would guess a Cortex M4 device. That would be my guess, because for this level of processing, I would guess that it could be a Cortex M4 right, or better, right? It was very interesting that I saw this audio codec. I wonder if this audio codec is a single device, or if he built the system himself, the codec himself, like the PGA separate from the ADC. But if this thing is a single device, this could be very good, because you could use I2S, which is a very common protocol to stream audio data to microcontrollers. And the SPI bus, you can see this is kind of an M4 like device, right? Or I don't know, M1, right? So you have two SPI buses and you don't have another one. So how could you stream the IF signal? So maybe this gives us a clue about what is the version of the STM32 that he's using. And then let's go. You have the output control voltage from a DAC that probably sets the output level control of the generators. Two generators, because one of them is low frequency and probably the second one is high frequency, and you get the second harmonic of the 4.4 gigahertz to go up to 8.8, and you high pass that to suppress the fundamental when you put the switch in position number 3 here. So you go to the directional coupler, which is 4-port. It's interesting that he chose to be the 4-port device and not to buy one which has the 50 ohm load inside. So probably he wanted to set up himself the 50 ohm load, which is something very good. So you can adjust the 50 ohm load to the precision that you want, right, to be as good as you want. So it's interesting. It's interesting to see that he chose 4-port directional coupler. And then the incident signal is down converted to the IF signal here, and you have the IF signal chain that goes to the audio codec. The audio codec allows to program the resolution bandwidth of this device, of the system, and in the software you'll see that we can select from 100 Hertz to a kilohertz of resolution bandwidth. And this is really good, because I don't remember if the Nano VNA could provide configurable resolution bandwidth, So this is really good. So you have the mixer for the incident signal as usual, and the mixer for the reflected signal from port 1 that goes back to the directional coupler, and then you have those low pass filters to get rid of the harmonics that are documented, all that mess that comes from the mixer. So that's why you need an LPF here, right, to get only the signal, the very, very low frequency signal in the hundreds of kilohertz, right, the tens of kilohertz, I believe. So you can see here that there are only 2 generators for the local oscillators, and you can see here that here he had to use an amplifier for the harmonic for the higher frequency of 8.8 gigahertz. So why he doesn't use that here for the local oscillators? because it doesn't need to, because if these are clock generators, which is very, very cheap to find these days, clock generators that go up to 4.4 gigahertz, the second harmonic of that, or you know, the third harmonic, it could be actually here, the third harmonic. So, because if it's a clock generator, it's kind of a square wave shape, right? So square wave, they have very small second harmonic. So it could be the third harmonic that he's using, or not. I don't know. We could start guessing right here, right? But you only need two, because the harmonic will already downconvert anyway, the higher frequency, and put it on the IF's incident signal. It's just a matter of adjusting gains and, you know, programming here the IF signal and processing later. So you actually don't need a third path in the LO, right? And then the port 2 is just a mixer for the transmitted signal, and then you downconvert that directly, and it's a very simple device. You can see that it's very simple because you can measure the leakage, the isolation of this mixer and all the input, the mixers from port 1, 2. So I'll show you on the spectrum analyzer how this signal behaves, what is the isolation of the signal generated to port 1, and what is the isolation from the LO of port 2 coming back, right? But I was pretty amazed at how this could calibrate well, because, you know, VNA is this is the beauty of the VNA. You can calibrate things out, right? So you can get a very good measurement, very good dynamic range. This device achieves, if I'm not wrong, 70 dB of dynamic range in the higher frequencies, right? Maybe 60 in 8.8 gigahertz. I don't remember well the specs. We can check it right here. So let's see if there's specifications. So it's right next. It's right here. So you can see. So up to 8.8 gigahertz is better than 65 dB. This must be typical. Oh, typical 75. Look at that. So this is a very nice dynamic range for a $340 device, right? This is really good. Of course, directivity, right, is not that good, you know, but the effectiveness after you look at the calibration on this. So this is really nice for many measurements that we could do. So pretty amazing device. Let's do some measurement to see how this behaves and to confirm everything that I told you about this branch here. You can measure the fundamental that is suppressed by this high pass filter. You can measure the LOs on port 1. You can measure the LOs at port 2. You can see how it's configured, this whole sweep scheme on the spectrum analyzer. The spectrum analyzer that I've got here, it's a Tektronix 306B. It goes up to 6 gigahertz. So in order to see the 8.8 gigahertz, I'll have to use a mixer. And I'll show you in a couple of minutes that too. But let's start with the low frequency and the high frequency generator and see if they are clock generators or not. And let's see. Let's check that out. Alright, so here's the setup to analyze the device. So I've connected port 1 to the spectrum analyzer. The spectrum analyzer is up to 6 gigahertz, so we're only going to analyze that bandwidth right now. I thought about using a mixer to show you the 8.8 gigahertz, but I think it's not necessary because you can see the behavior above 4 gigahertz, and you already see how it works. So there's no need just to do another setup just to show you that it's the same. But I've done that, believe me, it's just the same as I'm going to show you right now. So I'm going to show you on the spectrum analyzer on the PC. Let's start the software. So you can see it's a very simple software. There's not many features as the ones for the Nano VNA, but you don't need to, you know, you got the bandwidth. Select the serial port and connect. It takes some seconds. It's less than a minute. Okay, it's already working. And you can see, let me take the camera off. You can see that there are some LEDs indicating that it's working, right? Both ports. And then coming back to here, you can see, I believe it's good like this. So I've already set up as these 4 in the layout for these 4 plots. The right, in the top right corner, I have this S21, the phase of S21, log magnitude of S11 down here, and at the bottom right, the Smith chart. Okay, so as we're only interested in analyzing the sweep, the generators, I'm not going to worry about calibration. Okay, but you can see the menu, the initial menu is this one. Let me point out to the menu right there, and you've got scan. In the scan, we can control the generator, right? The plots, you can do any combination of, I believe, up to 8 plots in the same screen, right? You can select S11 or S21, Smith chart, polar, phase, linear magnitude, log magnitude, SWR, distance to fault, and loss, right? This is quite complete for each plot. Okay, you can set the SWR limit line just to help you if with a pass-fail test, and you can hide all the traces and show them. The traces you can save to a file, which is very interesting for later processing. The markers you can put up to, I believe, 8 markers here. You can set the frequency of the marker. You can put it to make the calculations for you. You can calculate the real and imaginary part, magnitude, phase, SWR, all that point in the plot, in the graph, right? It's really good. It's really handy, these calculations for the marker, right? Calibration, just regular open short close through. Device is just about version of the firmware and this software on the PC. You can check for updates if you want. Maybe they will update some features that we can see on the VNA. For example, the CW feature on the VNA is very, very nice to have. Like, you can use the Nano VNA as a signal generator. You can also do this, but I'll show you how I'm going to do manually, right? The settings is just language, and the directory where you're saving your files. So I'm going to use the scan to set the signal generator, and I'm going to pause the scan. So I'm going to set the span to 0, right? 0 span, and it works. It works, 0 span. The number of points, I'm just going to let it to be 500, doesn't matter. The resolution bandwidth, you can see if I put it at 20 Hertz. Actually, I thought it was 100 Hertz. I was wrong. I didn't remember that it was 20 Hertz. So you can see that it's very slow, right? Which makes sense. But I'll let it in 1 kilohertz. We not worry about that. 0 span. So to stop the sweep, for it not trying to be at the same frequency all the time, it will be flicking on the spectrum analyzer, right? So I'll just pause the scan when I choose the frequency. So let's choose the center frequency of 10 megahertz, right? And let's pause the sweep. Let's check the spectrum analyzer. And there you go. This is a 6 gigahertz span on the spectrum analyzer. So let me get the stop frequency to about 3 gigahertz. Maybe 2.5 gigahertz. There you go. So we can have our marker to the 10 megahertz. You can see the 10 megahertz is there, right? And you can see all the harmonics, right? Let us zoom in a gigahertz. You can see like 500 megahertz. Now you can see. So you can see the odd harmonics and the even harmonics, right? So he could actually use one of the even harmonics. But this is the low frequency oscillator, right? And the generator, let's say. I don't know if the local oscillator is the same low frequency of the signal source of port 1. But as you can see, the low frequency is like this. So let's increase the frequency to see when it switches to the high frequency if something changes. So I'll go back to full span. This is full span of this 6 gigahertz spectrum analyzer. I'm going to do like this. So let's reduce this screen. and let's start increasing the frequency. Let me put 30 megahertz. 30. And I have to play here to change the sweep, right? And then pause again. So we can see now, if I put a marker, peak, it's 30 megahertz. Okay, you might not see it very well. Let me take the camera and show it to you. So you can see this 30 megahertz, right? It's not exactly right, but I believe it compensates on the IF, right? So let's start increasing the frequency. Let's continue. Let me put 40 megahertz. Let's see what happens. And play here. Okay, and then pause for it to stop flicking. And it goes really well, right? It's working. I don't know if we can see when it's going to switch. Let's put 100. Play and pause. All right, we've got 100 megahertz signal, and you can see all the harmonics, and you can see the filter here, right? The filter is just lower harmonics. It's not showing that right here. If I increase the resolution bandwidth, decrease the resolution bandwidth to a kilohertz, for example, we can see much better that the harmonics, they still continue. There's no filter in here, right? But let me put it on 20 kilohertz just for us to get it a better update rate for this spectrum analyzer. So let's continue. Actually, I increased the span last time. Let's put it on 0. Okay, 0 span right now. Center frequency. Let's put it at 100. Play. Yep, it's there. Let's put it 500. And play. And so this is up to 6 gigahertz. Look how big are the harmonics of this generator, right? You can see that let's put a second marker to see. Let me add a marker, and I'll get this second marker to let me define the peaks. I'm going to define the peaks to be 55. Is on trace 1, yes. I'm going to define the minus 55, just for us to be tracking like this. So we can see, let me get the camera. You can see that this first harmonic, if we focus on there, it's 11, minus 11 dBm. And the second one is minus 46, right? So it's roughly 35 dB, right? 35 dBc for the fundamental from this second harmonic of 500 megahertz, right? But you can see you have all of them, right? Depending on the sensitivity of the receiver, you can actually measure based on the harmonics. So it's really cool. Let me put it like that. You can see the end of the screen. Let's increase the frequency. Let's put it up to a gigahertz. A gigahertz. Yep. So let's get the original marker to the peak. I have to pause. Didn't pause. Okay. Now it's paused. You got the peak. Let's get the other marker. So minus 41, the second harmonic, and the first one continues with minus 11.3. And this will go on, and you'll see that. Let me put up to 3 gigahertz. Let me play and pause. Let me put it to 299, actually 2900. Let's say 2900, just for us to see the second harmonic there. Okay, so the second harmonic is there, right? Because this spectrum analyzer is 6 gigahertz, right? You can see the second harmonic on here, okay? Let me help you. So right here, and this is the fundamental at 2900 megahertz. So when we start increasing, look at this. Let me play this, and let's put it up to 4 gigahertz. 4 gigahertz, okay, it's here, right? Let me pause that, and let me check with the marker. Peak, and it's measuring minus 9.7. It's actually a bit higher than the minus 11 that we were measuring before. So let me put it at 4.4. 4400. And okay, what is this? Look at this. Look at this here, right? So let me put the marker on there. Now, okay, a marker in there, and goes there, and the other marker, peak. So now we are seeing here at the frequency of 2.2, this one here that just showed up, we had nothing before going to 4.4. So now we have this thing here, which is half this frequency. And this frequency, this one here, let me focus on that. It's minus 16.6. It's not minus 11. So it's a different path. So it's that third position of the switch that I showed you before. You can go back in the video and you'll see that this is the second harmonic amplified, and this is the fundamental suppressed by the high pass filter. And we can see that it's actually better than 30 dB. 30 dBc, you can see the delta, right? It's better than 30 dBc, right? Which is fine, right, for most measurement. And if I keep increasing the frequency, let me focus on that. Okay, good. So if you keep increasing the frequency, for example, let me put, you see the 4.4 gigahertz here, right? Let me put 8.8 gigahertz. What do you expect to see here? So if I put enter and play, look at that. 4.4, exactly 4.4. This is the suppressed fundamental for the high pass filter, 4.4. And the 8.8 is not shown here on this spectrum analyzer because it's a 6 gigahertz spectrum analyzer. But this right here is the 4.4 gigahertz. And you can see that's what's remaining from the fundamental after the high pass filter, right? It's in minus 47 roughly dBm. The 8.8 gigahertz second harmonic amplified is out of the screen here because this doesn't work higher than 6 gigahertz. But I used the mixer and I saw that, and making the calculation, it's actually very good and amplified. So higher than, let's see, I believe it's higher than 4 gigahertz. It starts using that third branch, that third path. So let's go back to 4 gigahertz. So at 4 gigahertz, you don't see any half frequency. Actually, you start to see something here, right? But it's not at 2. Like 2 gigahertz is not right there. Yeah, it's around that. Yeah, it could be. Let's increase here. Let me put minus 10 on the reference level. Let's see. Actually, minus 7. Yeah, there is something in here, but it's very random, and the sweep is paused. So I believe it's only when it gets to 4.4 gigahertz. Let's see. 4.3. You see? 4.3, still nothing. Still nothing in half frequency. And then 4.399, nothing. Nothing on here. But 4,400, play, boom. We are on the second branch. We are on the harmonics right now. Here is the suppressed fundamental, and this is the fundamental. this is actually the suppressed fundamental, and this is the second harmonic amplifier. This is very nice, right? So let's see if we can measure the leakage. This is actually the signal coming from the generators, right? We're not measuring the LO at this point. So the leakage to the port 1 coming from the LO is quite good. We cannot see it here because in order to have IF frequency of kilohertz, the LO should be close to those frequencies that we're seeing right now at the signal source. So the isolation at port 1 is pretty nice, right? So let's check the isolation on port 2. So I'm going to do the setup for port 2, and let's come back here just to check the isolation and then start doing some measurements of characterization using the VNA software. Let's go. Alright, so I've connected the spectrum analyzer to port 2. Let's see if we can measure anything from the LO isolation to port 2. So, alright, there it is. You can see from the software I'm feeding 4.4 gigahertz, and we can see that we can measure that from the LO, which is roughly at the same frequency. And you can see that there's no difference from the fundamental to the harmonic because there's no third path in the block diagram for the local oscillators, right? So let's adjust this to the peak. So we have a frequency of 4.4 here, which is the second harmonic. It's actually using this second harmonic to down convert to the kilohertz IF frequency. And here is the fundamental coming from the local generators. But you don't see that high difference in amplitude of the powers from the fundamental and the... Maybe this is not amplified, right? So the other one was amplified, and the port 1 was amplified. So there you go. Here's the lead from local oscillators. Let's put it on a low frequency. Let's put it on 100 megahertz. Let's see. Pause. There you go. You have all the harmonics leaking from port 2. Alright, so that's it. Let's do some experiments and characterization of some devices up to 8.8 gigahertz. Okay, so let's measure some devices. Let's put in an attenuator from Mini Circuits, a 20 dB attenuator. I've designed here 4-to-1 RF combiner, power combiner, or 1-to-4 power splitter. You have some microwave filters on the path here, and you know, it's just a divider. Let's measure that. This divider is supposed to work up to 4 gigahertz. Actually, this is just an experimental prototype. It's not final yet, but let's check that. Let's also check this directional coupler from this company called Huber-Schneider, right? Up to from 800 to 2500 megahertz. Let's check that. And also, let's measure this small antenna that I've designed for the LP1 frequencies. It's between 800 something and 900 something. So let's check the tuning of this antenna. So let's see. So I've just calibrated the device and it's currently with a through connected. I'm going to show you because theoretically when you calibrate the through like this, basically the measurement plane comes right to the tip of the cable, right? So we're basically measuring how good it is, the input impedance of both ports of the VNA. So let's see how that shows in the software. So let me go up to this graph right here, which is the low magnitude. You can see that it's kind of good. This is the minus 10 dB line, right? So it's actually reasonable, right? It's reasonable. But if you put a marker, let me pick. So worst case here is minus 6.65, right? so what the through is seeing, right, from the calibration. So let's put the attenuator from mini circuits. Let's see how this goes. Actually, when putting the attenuator like that, I should have calibrated using actually a Mayo, right? A Mayo calibration kit. But the Mayo calibration kit hasn't arrived yet. So I'll have this little electrical delay here in the measurement, right? But it's all right. We know that there will be some difference because of the connector that I've put in here. It's not the actual attenuator, but you see that this thing is so good, so good. Let me show you on the screen. So look at this. Let me zoom in a little bit. Look at these two graphs right here. Right, look at the phase. Mini circuit standard, right? The worst case at 8.8 gigahertz is minus 12 dB of S11 magnitude, right? So it's a really, really well matched attenuator. And look at the 20 dB up here. So it's like 20 minus 19.8, and then worst case right here, minus 21.1 at 8.8 gigahertz. So what a nice attenuator. Not focused. Oh, better. Now it's much better. So you can see it's a very nice attenuator. Look at the phase here. Very linear, right? It's good. It's nice. So let's check the directional coupler. This one here. So I'll have to just put some N to SMA adapters before connecting it to that, and then get a load to put it on one of the ports. So I'll set it up and come back. Okay, so here's the directional coupler. I've connected the input port of the coupler to port 1 and the reflected port to port 2 and the calibration load at the output of the coupler. So let's check on the screen what we can see. So here we go. So let's check the frequencies. I'm gonna take the marker of this first graph right there, if I'm able to. Right there. So right here is 3.2.9. Okay, so this is the bandwidth. So from here is 800 megahertz. And let me put a second marker. I'm going to put first one at 800 megahertz and the second one at 2500 megahertz. So there you go. So this here is the bandwidth of the coupler with attenuation of 7.4 and 6.7. So this is 7.4 and this is 6.7. Reasonably good. And you can see that the S11 graph here, right below that frequency, is very well matched. So I'm going to get the camera here just to show you that. So you can see, if I focus on there, that's the attenuation. It's actually reasonable. And that bandwidth, and here is completely matched. Right, this is minus 20. It's minus 20. So you see, it goes up to minus 15 around here, which is basically 2500 megahertz. So works pretty well. Let's check an amplifier. Let's check a low noise amplifier as parameters in here, just to get things more exciting before the antenna, not only passives, right? Let's measure an LNA, next one. Okay, so I've just put here a setup with an LNA, which goes up to 4 gigahertz. This LNA has a gain of 20 dB. So as the maximum is 10 dB there, we've checked that the generator is going about minus 10, right? But I don't want to risk, minus 10, 20, and then 10 dBm to get to the limit of the port. So I put a 20 dB attenuator at the output here just for safety. So you subtract 20 dB from the gain that we're seeing in the S parameters right there, right? I'm using my power supply. Let me power up. The LNA is powered up. And let's focus on the screen. Let me get to the screen right here. Let's focus on here. Look at that. Beautiful curve. Beautiful. So let's check the 3 dB frequency. You can see, let me check the limits of this plot, the graph. Let me put it on right there. Okay. Look at that. The gain at low frequency is pretty high. You see, M1 is 6 dB plus 20 is 26 dB. 26 dB. That's why I put the attenuator in there. Let me see if I could get a log X, the X-axis. It would be nice to have it in logarithmic scale, right? Let me see if I can get that. I don't believe it's possible. The grid, yeah, that's unfortunate. If I knew how to put this in log scale on the X-axis, we would see that flat curve. But okay, let's see the -3 dB. It's actually very low frequency amplifier. 3 is around here, 400 megahertz. I don't know, it's got 10. Let's see at 4 gigahertz. It's got, well, 4 gigahertz. It's got like 7 dB of gain still. 7 dB. So maybe that's why they call that. But the S11 here, we can see that the bandwidth is from, you know, let me check here. Let's say -8 dB at 150, 160 megahertz. And marker 2, if I'm able, this is marker 1. Let me put it on here. Please go back, marker 1. Let's go to the markers. Oh, that's how I select them. Okay, they're not locked. Okay, select marker 2. Interface not that good to me right now. Okay, plots, markers, move. It moved. Okay, so 160 megahertz to about 3.5 gigahertz, something like that. It's advertised as 400 megahertz, actually 4 gigahertz in Aliexpress. But this is kind of a damaged one. I've already damaged this device, doing some soldering and everything. It's a very old device that I've bought. I do not take into account its specs anymore because I've used it for so many things. But still, the phase, look at that. It's really nice. And the impedance matching is quite good too, up to 3.5 gigahertz. So it's reasonable, right? And the gain from 7 dB here in the 4 gigahertz frequency up to 26, 27 dB, reasonable. You can also test active devices with this VNA. And finally, the antenna to finish this review. So, final experiment. I've got this Wi-Fi antenna, 2.4 gigahertz. So let's see the tuning of this antenna. Let me put the camera right to the plots, and let's get a small zoom in here. So there you go. Let me get the focus on here. Maybe, well, you can see 2.35 gigahertz roughly, the tuning of the antenna. So if you go up to 2.4, you could get -10 dB still. It works for the Wi-Fi, right? This is from a Wi-Fi router. So you can see that It's very reasonable tuning. Obviously, if I was to measure the tuning of this antenna, I would, zoom in here, do a calibration, and get many points around this point here to get a better precision in the measurement. Because here I have 500 points across the whole bandwidth, right? So this curve here is not very precise, but still, even in the full bandwidth of the device, you can still measure that the tuning is quite close to 2.4. It's 2.35 gigahertz with minus 20 dB of S11 on the antenna. So that's about it. Let me go back here to the device. I hope you guys enjoyed this video. If you have any tests, any measurement that you want me to test, I'll make sure to do a second video with a request from you guys in the chat. So leave below your comments of some experiment that you want me to test or to see if it works. So I'll do my best to get things that you need on the lab and do some measurements with this VNA. So let me know your questions. Give me a thumbs up if you like this review, and I'll give the link in the Aliexpress in the description. So if you want to buy it, so do it. I recommend the device. It's a very light device. It's not heavy at all. To me, it looks like the weight of a router. It looks like a router, isn't it? So all the best, and see you in the next video.